Hello there, my name is Tom and I will be presenting my research topic on nuclear thermal propulsion. I learn better from pictures, so I want to discuss this cover slide a little bit. This is a rendition of what a transfer vehicle may look like in the near future. The back section would be the reactor section. This middle section would be the propellant storage that can be removed and replaced. And this is the crew quarters. I hope this kind of grounds you a little bit about what I'm about to discuss. Here's an outline about what we're going to discuss. First, we'll talk about basic rocket theory and some important metrics used, benefits of higher specific impulses, and we'll talk about what specific impulse is, comparison between traditional combustion systems and NTP systems, propellant used in NTP systems, fuel type used in NTP systems, greater detail on NTP system layout and reactor design challenges, and we'll finish up with a conclusion. Spaceflight outside of low Earth orbits is going to require a substantially different paradigm of thinking with regards to propulsion systems. The focus on this presentation is on nuclear thermal propulsion, or NTP. Propulsion systems on rockets provide a thrust or force that moves the rockets. All propulsion systems provide the thrust through application of Newton's third law. For every action there is an equal and opposite reaction. This equation here is the rocket equation and is derived from Newton's second law, where delta V is the change in velocity during a burn or use of propellant. The velocity E is the exit velocity of the propellant. In reality, this is not a constant, and this equation becomes much more complicated in real application. MO is the initial mass of the rocket, including the fuel, and MF is the final mass of the rocket after the burn. Probably the most important metric for propulsion systems is the performance or efficiency of the propellant that is being used, and it is called the specific impulse, ISP. Here is a relationship for the specific impulse, and it's basically the thrust divided by the propellant weight flow rate, and it has units of seconds. Another relation for specific impulse is by coefficients, where CF is the coefficient of the exit nozzle efficiency, and it's basically related to the nozzle design or nozzle geometry, and C star is the characteristic exit velocity, where this term is the specific heat ratios of the gas. T is the exit temperature of the gas, and MW is the molecular weight of the gas. So as we can see, as temperatures increase and molecular weight decreases, your ISP, specific impulse, will get higher for a given nozzle geometry. So the goal is to get the ISPs as high as possible. So why is specific impulse so important? Well, the higher your specific impulse, the higher is your delta V, and the higher is your travel velocity. And that becomes especially important during long duration missions, such as a mission to Mars. For one, it reduces your overall travel time, less dependence on launch windows, reduced exposure to cosmic radiation for the astronauts, less exposure to microgravity to the astronauts, and because you're getting there faster, there's less payload needs for propulsion and more space for mission critical payload. And we'll talk about later, this is a typical launch trajectory for a mission to Mars, but it is very dependent on the windows to make the trip as short as possible. So now I'm going to do a little comparison between biopropellant chemical combustion, that's the traditional propellant system, and the nuclear thermal propulsion system. So first, the biopropellant chemical combustion system. As you can see in this diagram over here, this is a basic layout where you have a fuel tank and an oxidizer, and it takes both for this combustion to occur. You have pumps that pump both this fuel and oxidizer into a combustion chamber where it builds the temperature and pressure and then exhausts out the nozzle for the thrust. A typical biopropellant chemical combustion system has ISPs ranging from 175 to 300 seconds, depending on the fuel and design of the combustion chamber. Some examples are the SpaceX Raptor engines use a liquid oxygen oxidizer and a methane fuel, and they get ISPs of up to 300 seconds. And then an older rocket, Titan II rockets used back in the Gemini program in the mid-60s, the fuel used then was a tetraoxide oxidizer and Aerozine 50 fuel, and it had ISPs of 265 seconds. Nuclear thermal propulsion, looking at this diagram on its face, it's not very complicated. You have a propellant storage, in this case liquid hydrogen, that gets pumped through the reactor, picks up heat energy, converted to kinetic energy through the nozzle, and then thrust. So in a single chemical propellant system, you have a low temperature liquid hydrogen, and this is typically at 23 degrees Kelvin, turbo pumps, a reactor core, and the exhaust nozzle. This produces ISPs of up to 900 seconds or higher. And this is more than twice of what we see in ISPs for traditional combustion systems. Clear benefit to nuclear thermal propulsion. So what does that mean? So let's go back to the Mars mission. With a traditional propulsion system, the mission is at least 3 years, with launch windows only every 26 months, and a 7 to 8 month trip each way. With the higher ISP nuclear thermal propulsion systems, the trip is reduced to 45 days each way, with a much larger launch window, less restrictions. And this table here just shows different reactor proposals that are being worked on, but I wanted to point out the different ISPs that we see. 875, 906, 950, and this one here you can't see, but that's 1,000 seconds. So much higher ISPs, great benefit to the nuclear thermal propulsion over the traditional combustion engines. So why hydrogen? Well, here are some pros and cons of why hydrogen as a propellant is a preferred chemical. The biggest is the highest specific impulse of all the other liquid fuels, and that's due to its lowest molecular weight. As a comparison, we can see liquid hydrogen to liquid methane, 366 seconds to 330 seconds. Little to no coking and other forms of residual buildup, environmentally friendly, and it's non-toxic. Some cons: large fuel tanks are required. Hydrogen embrittlement, which is basically a corrosive property on metals when hydrogen is at high temperatures, and that will include the moderator material. It provides less thrust because of its lower molecular weight. Extreme cryogenic temperatures are required to keep it in a liquid form, and small size of the molecules makes it hard to contain through fittings and valves and other components in the system. But overall, its highest specific impulse is a driving factor. Okay, we've talked about the propellant. Let's talk about the fuel in the reactor core. There are basically two general types that we'll talk about, and that's the high enriched uranium and the low enriched uranium. Early on, most of the research was done with the high enriched uranium. And the primary pro for that is nearly all the atoms are fissile. And what fissile means is that all the atoms are capable of fusion, and it becomes a much more efficient chain reaction than a low enriched uranium. Cons to high enriched uranium are it is considered weapons grade. It does require government control, no commercial control, or usage is now allowed, and there's proliferation risk. Low enriched uranium, pros are it is allowed to be used commercially, and we do have it used commercially. This is the kind of fuel that we see in nuclear power plants. There's not or a low proliferation risk. Cons are that only about 1 in 5 atoms are fissile, so a moderator becomes much more important to increase the probability of chain reaction. So to date, most of the research is focused on the low enriched uranium process. Okay, here's a more detailed view of the nuclear thermal propulsion system. With any reactor, there is a coolant. So analogous to a nuclear power plant, the coolant is water. And that coolant is also the working fluid that turns the turbine and the generator. But that coolant also provides a cooling effect to the core, preventing it from overheating. So it's very critical to preventing damage to the fuel. In this case, the coolant is liquid hydrogen. It is also the working fluid or propellant. So liquid hydrogen starts out at a temperature of 32 degrees Kelvin. It gets pumped through a turbo pump and then distributed through passages in the core. Where it then comes back up and combines and then provides a motive force for the turbine that turns the pump. So at this point it's already been turned to a gaseous hot energy gas. The exhaust from this turbine then comes back down to the reactor and distributed, and now picks up even more heat and energy through the actual fuel assemblies themselves. Until it reaches the exit where it's about 3,000 degrees Kelvin. That heat energy is then converted to kinetic energy through the nozzle and thrust. A couple other things to point out. Off the pump branches a line that comes down, helps cool the nozzle, and then back up through the core, and that gets combined into the supply hydrogen gas to the turbine. And then off this supply hydrogen gas to the turbine is in a branch that feeds a electrical generating system. So this is typically a Rankine or Brayton type heat cycle. So the hot hydrogen enters, boils water to steam. Steam enters this turbine and turns the turbine that turns the generator, make electricity, condenses, gets pumped back, and continues its cycle. The hydrogen that gave off its energy now leaves, comes back down, and re-enters the cycle. A nuclear thermal propulsion system that has a electrical generating system is called bimodal. In other words, two modes: a mode for making electricity and a mode for making propulsion. We'll talk further about more details of the core in the next slide. Okay, now we're going to go into a little more detail about the reactor design. On the next slide we'll have pictures showing what we're going to discuss here. But first we're going to go through 4 items that make up the bulk of the reactor core. So the first item to talk about is the fuel support shroud. This consists of cooling channels, core structure support, and moderator. So in a typical nuclear power plant, the core structure is made out of a zirconium metal and the moderator is water. But on a nuclear thermal propulsion rocket system. We don't have water in the core, so the moderator and this core structure are one and the same. In other words, the core structure is made out of moderator material, which is typically some type of graphite that is a good moderator. Next item is the annular reflector. This also serves as the pressure vessel of the core and is made of a carbon beryllium. Now, the carbon beryllium has properties to prevent neutron leakage, prevents the neutrons from escaping the core. We want to keep as many neutrons in the core as possible to sustain a chain reaction. Next is the control drums. Control drums are integral to the reflector and are controlled and rotated with a portion of the surface being a neutron absorber that defeats fission, and the remaining portion being a neutron reflector promoting fission. This is how they can control the reactor power. And then finally, the integrated fuel assemblies. These are typically made up of a tubing cladding that holds the nuclear fuel pellets. The cladding is typically a zirconium material, and the fuel pellets are typically a uranium carbide material. All these having excellent properties to resist hydrogen corrosive attacks and high temperature capabilities. As we can see in this table, different uranium carbide, zinc, zirconium fuel options have very high melting temperatures. Okay, here we see some pictures of what we just talked about. We saw this before. This is the side view showing the channels and where the bundles are located. This is the top view of the core. The outside part is the reflector. And again, it is made of beryllium that reflects or keeps the neutrons inside the reactor. Here are the control drums. And you can see one surface is one material and the rest of it is a different material, and it is rotated such that it'll absorb or reflect neutrons back into the core, and that's how it's controlled. And then here's kind of an exploded view of a one of the fuel bundles. So you have a bundle, it's got several rods in it. Each rod has a cladded tube, a zirconium cladded tube with fuel pellets stacked inside. And that's the basic design of a fuel assembly and the reactor core for a nuclear thermal propulsion system. Now there's a lot of data, a lot of testing that goes into the actual geometry of the core. You know, some bundles are more reactive than other bundles, and they try to balance it out, but that's beyond the scope of this discussion. In conclusion, with the information presented, the audience was exposed to basic rocket concepts, biopropellant combustion systems, and nuclear thermal propulsion systems. Important metrics were discussed and identified, such as the delta V, delta velocity of a rocket engine, and the specific impulse. It became very clear the benefits of the nuclear thermal propulsion and the high specific impulses that it produced, such as shorter mission trips, crew safety, and less fuel payload. In general, we showed that the nuclear thermal propulsion system was not a complicated design. However, there still remains challenges as it relates to materials of construction in the reactor core and being able to withstand the high temperature corrosive properties of hydrogen. Hydrogen is the preferred working fluid, mostly due to its low molecular weight and increase of ISPs. Future research that would supplement this work is the study of nuclear electric propulsion, NEP, which can be used in conjunction with nuclear thermal propulsion. NEP uses a reactor to create electricity to an ion engine that generates electromagnetic fields that ionize and accelerate an inert gas to create thrust. The NEP used in conjunction with the NTP will only increase transfer velocities as the ISPs go up. Just as a final note, NASA and its partners are spending millions of dollars starting this year in 2023 for a planned nuclear thermal propulsion system demonstration launch in 2027. Thank you. Goodbye.